So let's talk about the concept of weight. The weight of an object near Earth is the gravitational force that the Earth exerts on it. Right? So weight is just another word for a force. It's measured in newtons if we're using SI units, just like any other force. Right? It's just another word for the gravitational force. And if we're first limiting our definition to being close to the surface of Earth, then this is just the force of the Earth on any object, right? It's the weight. If we're on another planet, we'll then define the gravitational force of that planet on that object to be the weight. We'll talk about that more in a few minutes. So in equation form, the magnitude of the weight of an object is given by this formula. Again, this is true only close to the surface of the Earth. But for everyday objects like us and airplanes and cars and everything around us, this formula is sufficient. All right, so weight, we'll use the symbol W for that. So the force of gravity acting on an object, or the weight, is equal to the mass of the object times g, the acceleration due to gravity, this constant of 9.81 meters per second squared. Okay. Now this is the magnitude of the weight. If we typically would define upwards to be the plus y direction, then the weight is always going to be down towards the center of mass of the Earth. So weight would therefore be in the minus y direction. And so the formula for weight in terms of a vector then becomes minus mg j hat. Right? It has magnitude of mg, but it's in the minus y direction. Okay. So to understand this equation a little bit further, let's now discuss the components of this equation, and first let's talk about m. Right? So what is mass? It's different than weight, right? Mass is not a force. Mass is just this intrinsic property of an object, right? In SI units, it's measured in kilograms, and this is based on the fact that objects in our universe are made out of particles, things like protons, electrons, and neutrons, and those particles have mass, right? This is a property that these particles have. In particle physics, these particles get this mass through the interaction with something called the Higgs field, but for the purposes of this class, all we need to know is that these particles have this intrinsic property like mass. Just like electrons have an intrinsic property called charge, they also have this built-in mass. Right? And so the mass of an object depends on how many of these particles make up the object. And so it's just objects around us have a certain number of particles in them, and that determines their mass. And so it's an observational fact that objects with more mass have a smaller acceleration for a given force. Right? So if you wanted to measure the mass of an object, say you're in space, and you wanted to measure the mass of an astronaut, how would you do that? Well, you could apply some standard force to that person and then measure their acceleration. The more massive they are, the smaller they will accelerate for that given force. Right, so mass is this built-in property. And talking about this equation a little bit more, so mass is this property of your object. It's a constant. G is this constant, it's 9.81. So this formula weight should be constant. If you're near the surface of the Earth, your weight should always be equal to your weight. Right? It doesn't matter if you're falling, or if you're sitting on a table, or if you're floating, or if you're hanging upside down, your weight should always give you the same number. Right? This is a force of gravity acting on you. And this is confusing sometimes because the equation for weight has g in it. Right? It has the acceleration due to gravity in that formula. But you don't have to be accelerating for you to have weight. Right? This is your weight even if you're sitting on a table, right? So that's a little bit of a source of confusion. So I'm going to try to explain how g comes to be in this formula. But first, let's just look at this in picture form. If we have a kilogram object which is falling, there's only one force acting on it, and that's the weight or the force of gravity. That's equal to mg. Right? If we have an object which is hanging from a string, it is at rest. There's two forces acting on it. It has a tension up, and it has the force of gravity or the weight equal to mg down. Right? So the weight is the same in either of these cases. In this case, this object is not accelerating at g. It is at rest. It has zero acceleration, but it's still, we calculate the weight using mg. Okay. So to talk more about where this formula originates, we can actually define a more general equation, and this is Newton's law of gravitation. Right, so this equation on the bottom here is a more general rule that is true anywhere, not just on the surface of the Earth. So if I plug in the numbers for the surface of the Earth here, like the mass of the Earth and the radius of the Earth, we end up breaking down to this formula, which we can use just on the surface of the Earth. All right, so I'm going to explain how that happens. Again, this equation, the force of gravity acting on an object, say I have object 1 and I have object 2, so this is a force of gravity on object 1 due to object 2, or the force of gravity on object 2 due to object 1. It depends on this constant capital G, which is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, multiplied by the mass of object 1 times the mass of object 2, divided by the distance between those two objects squared. All right, so this is our more general force equation for the force of gravity. To talk about this equation a little bit more, Newton's law of gravitation, I can read it out in word form. Every particle of matter attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Right, so that's describing this equation in words. So if I have two particles or two planets, or in this case a planet and a moon, the magnitude of the gravitational force of the moon on the Earth is some number, right? So this is the moon is actually attracting the Earth towards it with some force, and the Earth is attracting the moon towards it with the same exact force given by this equation, right? So the magnitude of these two forces are exactly the same, right? Why is that? Because m1 is the mass of the Earth, m2 is the mass of the moon, r is the distance between these two objects, and so this is the same for both of these objects, so I get the same force of gravity. Okay, so again, the larger the masses, the bigger the force, right? So the force is directly proportional to the product of their masses. So if I make the masses bigger, the force becomes bigger, and it's inversely proportional to the square of the distance between them. So if I make the distance larger, that's in my denominator, so that makes my force smaller. Okay, so this is a more general rule. Now, if we look at the particular case of us being on the Earth, so say this person is just running on the Earth, and one moment he jumps in the air, right? This person on the Earth who seems to be a giant. We could think about what is the sum of forces acting on that person, and set that equal to mass times acceleration using Newton's second law. And so if that person is jumping in the air, the only force acting on them is the force of gravity, given by now this more general equation, g m1 m2 over r squared. So I can plug that in for the net force here, because that's the only force, and I get capital G times little m, the mass of the person, times the mass of the Earth, divided by the radius of the Earth squared, and that's equal to the mass of the person times their acceleration, right? And therefore the acceleration of this person is just G mass times the Earth over the radius of the Earth squared, right? Because their mass is canceling out. And it's this acceleration which we are just going to call little g, right? So we're just going to give this number a special name and a special symbol. We're going to call it little g. So this is how 9.81 meters per second squared originates. We multiply this constant g, capital G, times the mass of the Earth divided by the radius of the Earth squared, and that gives us our acceleration due to gravity, right? So that's where that originates. Now if I take my force of gravity formula, my general one, I pull out the mass of the person and replace m2 with the mass of the Earth, replace the radius with the radius of the Earth squared, right? This is again our constant little g, so this is where our weight formula comes from. The force of gravity is equal to our weight is equal to m times little g, where little g is this bunch of constants, right? So this gives us a little bit more idea of where this simple formula, which is true only near Earth, comes from. Right? If we're assuming that we're at a distance from the center of the Earth equal to the radius of the Earth, meaning we're on the surface, then this is true. Okay, and so when I'm solving problems using this formula, it's almost helpful to think about little g as just being a constant and just forgetting that it's equal to acceleration, because that causes confusion. Right? This is true whether or not you're accelerating or not, and so it may be helpful to you to just think about little g as just a symbol which means constant 9.81 or a bunch of these other constants, right? It's just some constant, okay? So I hope that helps a little bit of the confusion with this formula. Now, a little bit more about weight. So your mass does not change if you travel from Earth to Jupiter, right? As we talked about, mass is an intrinsic property of an object. It depends just on what particles you have and what mass they have. It's built into those particles. So that doesn't change if you go to Earth, from Earth to Jupiter or the moon or somewhere else, right? But your weight does change, right? Because the force of gravity acting on you on a different planet is going to be different than on the Earth, right? If we found that our constant little g is equal to big G times the mass of the planet divided by the radius squared, then we can calculate g, the acceleration due to gravity, on other planets. Right? On Earth it's 9.81, on the Moon it's 1.6, on Mars it's 3.7, and on Jupiter it's 23.1. Right? So this tells me that my mass is the same on any planet, but my weight is going to be different depending on where I go, right? Based on this formula. My mass is the same everywhere, but I plug in different g's, I can figure out my weight on different planets, right? So on Earth, the force of gravity pulling down on me may be one number. On Jupiter, it's going to be at least 4 times larger or so, right? Or 3 times larger. Okay, that's mass and weight. Mass is the same anywhere, weight changes. Weight will also decrease as you increase in altitude above the Earth, right? Because little g depends on some constants divided by the distance between the two objects squared. So if you're on the surface of the Earth, this is just equal to 9.81. But if you travel above the Earth, right, in an airplane, or you travel up into space, little g is going to get smaller because this distance is going to get larger. So we can actually plot little g as a function of height above the Earth, right? So near the surface of the Earth, it's 9.81. As we go up just a little bit to the top of Everest, we're only 4 kilometers high, and you can see this is 50 kilometers here, so 4 kilometers is really close here. So the g will be slightly smaller on top of Everest. If I go up in an airplane, I'm now 10 kilometers high, so g will be slightly smaller. It may now be 9.79 or something instead of 9.81. And if I travel up to where the space station is, 300, 400 kilometers above the Earth, g is actually more like 8.7 meters per second squared at the space station. Right? So g is decreasing with altitude. So this leads us to our next concept, the concept of apparent weight and apparent weightlessness. Right? So if you're in orbit, you're floating around in the International Space Station, g is still 8.7 meters per second squared for you. It's only a small fraction smaller than it is on Earth. Right, so if you weigh 140 pounds on Earth, you weigh 123 pounds on the space station. Right, you still have a pretty large force of gravity pulling down on you if you're in the space station. So why does it seem like you're weightless? Right, this astronaut is floating around. Right, this lettuce is floating around. Why does it seem like you're weightless if you still have this large force of gravity pulling down on you, 123 pounds? Okay. So the answer is that if you're in space and you're orbiting the Earth, you are accelerating. You're continuously falling. You have this centripetal acceleration towards the Earth as you move in a circular path around the Earth. So this acceleration leads to something called an apparent weight, which is different than your actual weight. So, and 2 other nice examples of this, so you've probably felt this before at an amusement park. If you suddenly drop and your stomach rises up in your body, or you may feel weightless for a second as you drop on a roller coaster on one of these rides. You can also, for a lot of money, pay for a trip on this zero-G plane, which goes on these really interesting parabolic paths and gives you like 30 seconds of weightlessness or something. So sometimes they shoot movies and things in these airplanes, and you can watch a fun video of that here if you're interested in that. But you can have apparent weight or apparent weightlessness on Earth by basically falling, and while you're doing that, you kind of feel like you're weightless. So to explain why this is, and we can talk about the kind of most common problem where we get to deal with this type of situation, we can collectively call these elevator problems, but these are really true for any kind of problem where you're accelerating and you're trying to calculate the force acting on you. Okay, we have an elevator here. On the floor of the elevator, we have a scale, and on that scale, we have a dog. All right, so what does the scale read? So just in general, a scale does not tell you your weight. A scale tells you the force of the dog on the scale, or the force of the scale on the dog, right, by Newton's third law, which could be different than your weight if you're accelerating. To explain why that is, let's define a certain situation. Let's define the plus y direction to be up. Let's say this elevator is accelerating upwards in the plus y direction, and we can draw a free body diagram for this dog. There's a weight down, that's a constant, it just depends on the mass of the dog, and g, right? And then there's this force upwards causing the dog to rise up with the rest of the elevator, right? That force upwards is, I'll just call it the force of the scale on the dog, because the scale is what is pushing up on this dog to cause it to accelerate upwards, just like the elevator. right? And so if this dog is accelerating upwards, it must be that we have unbalanced forces acting on the dog. It must be that the force of the scale on the dog is bigger than the weight of the dog, right? This has to be bigger such that the dog is accelerating upwards. So if I use Newton's second law, I plug in what is my sum of forces acting on that dog. Well, I have one force in the plus y direction, that's the force of the scale on the dog. I have one force in the minus y direction, which is my weight. And then the sum of these forces gives me the mass times acceleration of that dog. So I can solve this for the force of the scale on the dog, and it's equal to the mass times acceleration of the dog plus the weight of the dog. Right, so what does that mean? It means that a scale is not going to display a number equal to the weight of the dog. The scale is going to read this number, the weight of the dog plus the mass times acceleration of the dog. Right, so the scale is, since the scale is pushing up on the dog, it is not going to read just the weight of the dog. It's also giving the dog this acceleration, which is going to make this read a larger number. Right, so this is what we call apparent weight. And you may have felt this before in an elevator. You may feel heavier as you're accelerating upwards in an elevator. And so if we take this to a very special case, say now our elevator is accelerating downwards, okay, in this case. Oh, I should have changed my free body diagram here. I'm sorry. Let me get rid of these forces for now. I didn't do that. So, okay, let's talk about what's going on in this case. If we're accelerating downwards, then I can take the same formula we had just derived. The force of the scale on the dog is equal to the mass times acceleration of the dog plus the weight. I can replace weight with mg. That's always going to be the case near the surface of the Earth. And I can replace my acceleration with negative g, right, because that is the acceleration of this elevator and therefore this dog. And so I have minus mg plus mg, and these cancel. So I have 0. So in this case, the force of the scale on the dog is equal to 0, right? And I shouldn't have gotten rid of my weight vector. Maybe I'll put that back in here for you. So in this case, the weight of the dog hasn't changed. We still have this force of gravity acting on the dog, but the actual force read by the scale is going to be 0, right? The scale is going to not tell you your weight. It's going to tell you 0 because the force of a scale on you is 0. It's falling away from you as you're falling, and basically the scale is going to read 0. So this is the concept of apparent weightlessness.